So I'm from the Oak Ridge Leadership Computing Facility, so everything I do is usually geared towards, getting an effective simulation on the highest level computing we have. And I'm in the scientific computing group, so I kind of sit in the nexus between applied math, climate science, and computer science. And really, I don't belong in any field, and yet I'm in all of them. But the topic I want to talk about at first is, why is accelerated computing difficult to use? And most of us probably know these reasons. I just wanted to give you my biggest concern as to what's going on in these machines. If we consider the fact that we have to reduce power consumption, usually that means you have to cut down on the power-hungry cache that's available on node. You have to slow down the memory clock, and you have to make the memory bus wider. There's other things that have to happen as well, but really the crux of it is right here. The compute power is significantly greater than the bandwidth. And so as an example of this, the NVIDIA V100 GPU is capable of 15 trillion floating point operations a second in single precision, but it can only feed about 225 billion floats per second. And since most of our arithmetic operators are binary, they require 2 pieces of data, so really the memory bus is about 130 times too slow. That, to me, is the real problem that's going on. That's what I'd like to address algorithmically. How do we handle this? So there's a lot of people who say, hey, we're back at vector computing, yay. But sure, it does have a lot of similarities to the old school vector machines in the sense of pipelining instructions. But if we look at the Cray 1, for instance, and yes, this came from Wikipedia because I was born in the 1980s, not the 1950s. So it could do about 160 million operations per second, but it could feed about 20 million pieces of data per second. So the bandwidth in this case is about only 16 times too slow. So yeah, we've been here before, but I would argue that I'm not sure we've ever been here quite this extremely when it comes to the disparity between how much you can pump stuff into that processor and how fast it can actually do the processing. So what does that mean for our algorithms? Number one, when you fetch a piece of data, you really need to do as much with it as possible. It's never been more true that once you grab a piece of data, you can do almost anything on that data. As many operations as you can possibly imagine, and you're probably not going to pay for them because you paid for the data fetch. So this is an idea called compute intensity. GPUs have an increasingly small amount of fast on-chip cache, which is painful and it sucks, but welcome to the brave new world, right? So you want to load a small amount of memory from main memory, and you want to perform as many computations in cache as you can before you write that stuff back. So we're going to look at that from an algorithmic perspective. And really, I'm just going to demonstrate one algorithm that I tend to favor, but please generalize the concepts. We also need less algorithmic dependence. So every global synchronization has a pretty high cost, and the reason is that it kicks your data out of cache. So every global loop through your data that you have on node has roughly a fixed cost. The cost of the loop depends on how many pieces of data you're having to touch cold from DRAM. So you pay for these out of cache memory accesses, not the computations. So you don't want to have too many places in your algorithm where everyone has to get at the same part before you can enter the next loop. And we'll talk a little bit about that from an algorithmic perspective as well. And finally, we need to move less data over the network because the network is slow as all get out, and it's the latency can be quite high and the bandwidth can be quite low over network, especially compared to on-chip memory accesses. So we want to reduce those as much as possible as well. So I'm considering atmospheric dynamics from the Euler equations. It's kind of Navier-Stokes because you always have some sort of implicit damping in the numerical scheme, but there's nothing explicit that I add in this case. And for those who hate equations like I do, here's a pretty picture of the Euler equations. So I'd like to start with like an upwind finite volume discretization in space. I like this algorithm for a number of reasons, but first I'll describe it, even though most of you probably know it, but the solution is described as a set of non-overlapping cell averages. And the cell averages update based on cell edge fluxes, and you use a Riemann solver to reconcile 2 different estimates of the flux at the same interface. That Riemann solver being upwind is what adds the necessary dissipation to the scheme to make it stable. And if you want high order accuracy, you reconstruct the variation within cells using a stencil just by straightforward polynomial interpolation. What I like about finite volume, it conserves all of the variables in the conserved vector to machine precision. You can use a nice large time step of a CFL of 1, which there are very few Galerkin methods that can match this at high order accuracy. That's the crux. At low order, Galerkin will do better. And it treats every degree of freedom individually, unlike element-based methods. And while that is more costly, again, we're not that worried about computations as long as they're in cache. And it tends to give better accuracy in a limited context when you treat each degree of freedom individually rather than treating them in blocks. And as long as you don't have shocks in the Euler equations, it's stable without the need for added dissipation, which also can be very difficult to achieve for non-Upwind finite volume methods and for finite element methods as well. I like to use weighted essentially non-oscillatory. This is the next part of the algorithm. Especially for transport, this gives a really nice solution to discontinuous problems. The gist of this is you compute multiple polynomials, and when the data is smooth, you revert back to the high order, and when it's non-smooth, you revert to one of these three, and it's a weighted combination of these. And you calculate the total variation of each, and if one's really highly variable, you weight it lower so that it doesn't cause your solution to oscillate. The beauty is, you see that same stencil there, it doesn't require any additional data when it's used with finite volume. You can use the exact same stencil that you had before, and it's very accurate and effective at limiting oscillations. There's a custom implementation in a paper in James from Ram Nair and myself that improves upon traditional Wino applications. In ours, it actually improves the accuracy for smooth and non-smooth flows, no matter what, in every context, which is pretty rare for a limiter to increase accuracy, because usually the dissipation decreases accuracy. And finally, we use something called arbitrary derivatives in space and time, or ADER. This is a time discretization that recognizes the PDE itself translates spatial variation into temporal. And we can also see that from the equations that we saw earlier. You have a time derivative, and it's based on a set of spatial derivatives. So you're just translating variation from space to time. That's the ultimate goal of the equations. So you can imagine here for just linear advection equation here, if you have more spatial derivatives up to higher order, then you also have higher order time derivatives. And the fact is, you can calculate these without using multiple stages or multiple steps. And so there's no additional data required. I put that in bold because that's the most important part of this. You get high order at a large CFL number of 1 without multiple stages like Runge-Kutta. It automatically propagates Wino limiting through the time dimension because your time derivatives are based on the spatial derivatives, which are themselves already limited. And it's more accurate than a lot of the existing ODE integrators. I haven't seen a Runge-Kutta algorithm that give this even near the same accuracy as ADER at the same time step in order of accuracy. So those are the three pieces of it. If we put it all together, this is the algorithm summary for this dynamics approach. You reconstruct variation using the stencil, say 5 cells, 5th order accuracy. You apply Wino limiting using the same stencil of information. You compute ADER time stepping by translating these spatial derivatives into time using something called differential transforms, again, using only that small chunk of data. So nearly all of the computations in the model, this is where all the compute intensity is. This red line is your first global algorithmic barrier. So you can do all of these in cache in memory without having to touch DRAM multiple times. So this is a particular algorithm that really clusters computation with a very small amount of data dependence in memory. So as far as accuracy is concerned, we all have this concern that we can go high order in the atmosphere, but the atmosphere data is somewhat discontinuous, and therefore you're not going to get high order convergence, but I would argue you still get a better constant of error. And to demonstrate this, these are both using Wino limiting, and we're going from 3rd to 9th order, and you can see that the scale, the spatial scale at which you're resolving these turbulent eddies is finer. It's visibly so. You can see it in the kinetic energy spectra as well, though I didn't plot them here. But something that I want to really point out is that the 9th order has 6 times more computation than the 3rd order, but it's only about 50% more expensive when you run them on GPUs. And the reason is that once you grab that data, the computations, you don't really pay for them so much. And then we consider the idea of robustness. In this case, we have two thermals that are colliding into one another. You have a warm and a cold, and they crash in the middle. And you can see these little oscillations that are happening here. This is without we know limiting. I should have put that as a label, but that's all good. And then you add we know limiting, and you can see that these oscillations are significantly reduced. And that's the goal of it. Now you're wondering, how much are they reduced? Let's just cut a line through the middle of the domain, and we can look here. That's what's happening when you apply the we know limiting. It's not really touching anything except where those oscillations are occurring, and it will reduce extrema somewhat. And if we look at the kinetic energy spectra, power density, the red line is no limiting and the black line is we know. You can see that these two are right on top of each other right until the very 2 delta x mode, which is the finest resolved on this grid. And so really we aren't affecting the solution on the coarser grid very much at all. We're really only affecting the 2 delta x, and we're leaving everything else alone. And this is demonstrating that we know is an extremely accurate way to limit. And something I want to show here is that without limiting, we ran about 26 seconds in the wall time, and with we know we ran about 30 seconds. So this is only a 15% change, but we know has 16 times more computations than no limiting at all. And I used hardware counters for those, so I know that is the actual increase in computation. So this is truly demonstrating that you can add a lot of computation to your algorithm, and you really don't have to pay for it. A lot of that stuff comes for free as long as you do it within cache. And doing it within cache on the GPU is increasingly hard, so we need algorithms that take a very small stencil-based chunk of data and just go to town on it before it writes back to main memory. If we consider performance on the NVIDIA V100 GPU, the most expensive kernel that does those 3 operations you saw in bold in the slide before, it gets about 80% peak flops, which is what you'd typically expect from LinPack. I mean, this is a very high flop rate. We're getting about 12 trillion operations per second in that kernel if you give enough work. And on the AMD MI60 GPU, we're getting 40% peak flops. We use the HIP backend to port to there. And I'll get into that more in a second. The reason for the disparity here, these are actually 2 very comparable GPUs, but the NVIDIA does a much better job with caching. And that was on purpose. They designed the chip itself to make you rely on the cache more and have to do explicit shared memory less. So it's a much more convenient chip. So I'm hoping AMD will catch up, you know, in their hardware. And there's also independent thread scheduling and a few other things that happen on the V100 that don't currently happen on the MI60. So we use a C++ approach to performance portability. We specify our kernels as C++ lambdas, and I'll get into what that actually looks like in a little bit with the code example. But the kernel describes the work of a single thread, and basically this is simply CUDA with a different syntax. You say, here's my kernel that operates on 1 thread, here's how many threads to launch, which is exactly what you do in CUDA. And once exposed, the parallelism is very portable across architectures, but the burden is on you to expose that parallelism. And I don't think you're going to get around that for any given application. There's no way to get past the notion that you have to tell the compiler at some point where the parallelism is and how to express it. I use custom multidimensional array class for the data, where we bind the dimension sizes of the array to the object itself. So in Fortran, you can change that at the call site. But in C++, in this instant, we actually bind the array's attribute to the object, not the call site. So you can't override these. So you get very robust array bounds checking. And we use something called shallow copy for GPU portability. If you want to use a lambda, you have to do something capture by value. This is getting into the weeds for non-C++ folks. But there's a certain way you have to copy the data structure when you pass it in. And so we just run the launcher for the kernels on multiple backends. And so here's an example of some C++ code that does a Runge-Kutta update is what's going on here. So we have a loop over state variables and then Z, Y, and X. And we're just updating the state based on some tendency in the previous stages. And if we were to run this, so if you really want to see what's going on, we have a set of parallelisms that you're expressing here, and then we have the kernel that's going on here. And so if you wanted to express this with something like that looks like Cocos or Sickle or HC or any of these languages, they're all pretty much the same. you need parallelism, and you need a kernel. And so what it looks like here is you're saying how many threads I'm launching, and then you unpack these indices into multiple dimensions, and here's that same kernel. And you'll notice that the actual kernel code is identical in every way. So really all that's happening is you're changing the way you express the parallelism. And because I do personally think this is kind of ugly, I like to leave the loops commented in when I port a code over so that it's very clear to the reader what I'm doing. So if I were to take this function here, so you see that I've created what's called a lambda. This is basically just, putting this code kind of in line. If I pass this lambda to a launcher and I want to run it on the CPU, then, whatever this function is, f, I just run it within a simple for loop. And if I want to run it in CUDA, then I do a kernel launch of this function f, with the CUDA kernel that makes sure that it stays in the right bounds. If I want to run it on the AMD backend, I do the exact same thing as CUDA. I just replace CUDA with HIP. And it's really nice. So we have this working on at least 3 backends. We're going to add OpenCL soon. As far as what we are currently doing on the GPU, so we have a cloud dynamical core that needs some work before it's actually useful. But it's running on AMD GPUs already using a custom-made kernel launcher called Yet Another Kernel Launcher, because YACL rolls off the tongue, It's very similar to Cocos. It's just super duper simplified. And we will transition to Cocos once they have AMD added to their backends. But we wanted to go ahead and run on there now. There's a code called MiniWeather that's a training app. It's about 400 lines of 2-dimensional, simple atmospheric dynamics that is running successfully on AMD GPUs in Fortran using OpenMP4.5. That was something very surprising for us that we're actually getting the right answer for that out of the box. And it's very encouraging that maybe this will actually be ready when Frontier hits the ground. There's a project called Scream. And they have physics packages that are already using C++ and Cocos. They're transferring them over now. And once Cocos has a HIP backend, those are going to run just fine on AMD hardware. And we're going to link that up with whatever die core we choose for the cloud model. And we are constantly sending kernels to both AMD and Mentor Graphics. I should have put Crane here as well. I found a repo for the UKMO's Cyclone kernels that they've generated, and we're also going to have our ROTMGP radiation package ported over soon. So we're sending this stuff to the vendors to make sure ahead of time that they know, and we could send it to ARM too. I see you shaking your head. But we really want to make sure that vendors know what our code is and know what our needs are and are meeting those as they develop it so that once the machine hits, it'll work. Now, something that is antithetical to everything I've talked about so far is the idea of stiff acoustics. You have grid spacings down to even 10 meters or less near the surface in the CESM and the E3SM because we really want to capture dynamics that are happening at the surface more finely than what we capture aloft. And if you look at the grid spacings there, it's at least 100-to-1 aspect ratio. But the wind at the surface is really only about 1 meter per second because even convection hasn't had time to really generate much vertical motion. So you're looking at a stiffness of 1 meter per second versus 370. So clearly we can't bow down to the time step that's enforced by acoustics. So you had to find a way around it. And the most common approaches are, do some sort of upwind implicit acoustics. I should have put implicit up here, where you do some sort of IMEX coupling. If you wanted to do this first order, you'd have about 4 tridiagonal solves per time step for that. Another way to do is increase the speed of sound to infinity, and you end up with a Poisson solver for pressure. And you diagnose density and update the rest of the variables from that, and that takes 1 tridiagonal solve. Another approach that we've already heard here is you could do some sort of like high order implicit, fully coupled vertical solve with something like Jacobian free Newton-Krylov or some other iterative approach. Those have the potential for being better on a GPU because you can do them at high order accuracy, but they require many loop iterations through the data, and I really don't think it's going to be worth the cost personally. So the best thing I can think is just to accept the fact that it's not going to be compute intensive for the implicit acoustics and just do it as quickly and accurately as possible and jump out of there so we can go to something that technically matters more, which is the explicit affected dynamics that run slower. And so that's everything I have for the presentation. So I'll take any questions at this point. Thanks for listening.